Alright, here we have lecture 1.3, which corresponds to section 2.4 from the textbook. This is a short lecture over complex numbers. Turns out complex numbers aren't all that complicated. So recall, anytime you have a negative inside of a square root, that value is not real. So what we're going to do is we're going to go ahead and define I to represent the square root of negative 1. And we use the letter I because it corresponds to imaginary numbers. So your high school teacher may have described these as imaginary numbers. Imaginary numbers, complex numbers, they are synonymous. Now, what's interesting about complex numbers is they are two-dimensional in nature. So, a standard number is a one-dimensional value because all real numbers exist on a number line. So you can view the real numbers as a kind of one-dimensional space. Complex numbers, if you look at this, it's what we call standard form. So standard form of a complex number has two parts to it, the a plus bi, where a represents the real part, b represents what we call the imaginary part because it's the coefficient of the I. So that actually gives complex numbers a two-dimensional nature. So we can't plot complex numbers on a line, we actually plot them on a plane. Now we're not really going to be playing with the complex plane in this course. That kind of, goes a little bit beyond what we do in college algebra. But know that the two-dimensional nature of complex numbers makes them very, very useful to electrical engineers in particular, especially when you throw in something known as Euler's identity, one of the most important formulas in, all of science. We won't be getting into Euler's identity because it requires some trigonometry, so that's, again, well beyond the realms of this class. But know that complex numbers, or what you call imaginary numbers, actually have some really real applications. Particularly, again, electrical engineering is my favorite example. They really simplify a lot of work in electrical engineering. But there, just a little bit of history on complex numbers. It is believed that complex numbers originated from the Italians, when the Italians were trying to solve cubic equations. So it's kind of an interesting little history I encourage you to look into. But the fundamental theory of complex numbers as we know them today was derived primarily by a man named Gauss. But enough with the history, let's go ahead and look at it. So just a quick heads up, whenever you encounter negative inside of a square root, and I stress the square part of the square root, go ahead, factor out that square root of negative 1, switch it out with an I, and do that before you proceed. So let's look at some examples. So we have negative square root of 4. Notice the negative is not inside of the square root. This is not an imaginary number, it's a real number. Negative root 4 is just negative 2. Now here, we do have an imaginary number. Note we have the negative inside of the square root. So when we simplify that, that simplifies into I root 4, which reduces to 2i. And if you wrote I2, that's fine. I2, 2i, same thing. And then this one will simplify to negative I times square root of 4, which reduces to negative 2i. So anytime you see negative inside of a square root, ditch the negative, replace it with an I coefficient, and you'll be good to go. So here I see number 4, a negative inside of a square root, so ditch the negative, replace it with an I, and then we'll go ahead and simplify that, so that will simplify into 5I root 3. I'll send them. And if you need a little refresher there, that's simplifying radicals. And then this will simplify to I root 8. Square root of 8 reduces to 2 root 2. Now be very, very careful with example number 6. Note that this is not a square root, it's a cube root. So this is not imaginary. That's because it's a cube root. So you have to make sure you're paying attention to what type of root you're working with. The complex numbers are going to be coming from square roots, not odd roots. Now let's go ahead and look at deriving powers of I. So we know by definition I is the square root of negative 1. Now this is an equation, and keep in mind with an equivalence relation we can do whatever we want to that relation so long as what we do to one expression we do to the other expression. So if I square both sides, I get I squared equals, square root of negative 1 squared is just negative 1 because squaring the square root cancels. And then we can keep going with this. I cubed, by definition, is I times I times I. But we know every pair of i's is just negative 1, so that's negative 1 times I, which is negative I. And we can do I to the 4, so that's I times I times I times I. So we can pair those off. So that's negative 1 times negative 1, which is positive 1. And we can continue doing this. We can look at, say, I to the 5th. That's I times I times I times I times I. And every time we have a pair of i's, that equals negative 1. So there's a pair, there's a pair. So it's negative 1 times negative 1, which is positive 1 times I is I. And you can see we get right back to the beginning of the loop. If I do I to the 6, you can view that as, 3 pair. So negative 1 cubed is negative 1. And you may notice that it's going in a loop. So there's actually only 4 powers of I you need to know. You got the original I squared will always simplify to negative 1. I cubed will always be negative I to the 4th equals 1. So you don't really have hypercomplex numbers. Every power of I simplifies back down to either a real number or I to the 1st, which is quite nice. It's a very nice property of complex numbers. So we'll use that to do problem 1. So we know square root of negative 4 is I root 4. Square root of negative 9 is I root 9. So that simplifies to I squared times 2 times 3, which is going to equal negative 6, all said and done. So you have to, first step, replace that square root of negative with an I, and then use those powers of I here. So we're going to do number 2 now. And we're going to go ahead and replace, anytime we see a power of I, we're going to simplify it. So we know I cubed is just negative I. And we know I to the 4th is just 1. Okay, that simplifies quite nicely. So then we have 36. Now it's just a matter of order of operations. Minus 1 plus 3 is 4. So all said and done, we get 32 minus I. Alright, last example for this lecture. Like I said, it's a short one. So here you just want to multiply like you normally would. Go ahead and distribute. Many of you like to use the FOIL acronym for describing the distribution when multiplying two binomials. But let's go ahead and multiply here. 2 times 3 is 6. 2 times negative I is minus 2I. 3 times I is 3I. And then positive I times negative I is negative I squared. So that's 6. Negative 2I plus 3I is 1I. Minus I squared, which is negative 1. So minus negative is positive, and we get 7 plus I, all simplified. Alright, so let's go ahead and look at, I'll save those examples for the quadratic formula in the next section. So that is a wrap on complex numbers. Like I said, it went by pretty quick. And you're now ready to handle another chunk of worksheet 2. So the next lecture is kind of a long one. It's a big one. The next lecture is going to be over quadratic equations. And once you cover that lecture over quadratic equations, you'll be ready to finish up worksheet 2. All right, keep up the hustle and have a wonderful day.